have a So we started the presentation. So this is what we call restructure. And the whole idea is looking at non-linear doubly curved surfaces, doubly curved structures in a different look altogether, and how we can make do with the structural system and create something which is entirely a new structural system probably. So before we go through, there is a quick intro of what we were talking about. So the project is about a student housing in an abandoned oil rig in Netherlands. We're talking about the student housing which is entirely in a really dramatic scenario where you have a different context, you have a different kind of user, and it's a different scenario altogether. So I'm really tired. So we are talking about a design approach which is either energy driven or functionality driven. So the idea was to combine the whole different branches of the tree and bring together and in unison design something which will be a user friendly, a functional oriented, a user customizable design. At the same time, the main functions of a student, that's what we all do. We work, we sleep, we cook, and evolution, and again work. So the whole program should revolve around this whole movement. The site, interestingly located in the middle of the sea, receives most of the times really cold winters, extremely cold winters, and mild, warm summers. Most of the times, as you see in the red zone, it's the blue zone that's in the comfort zone, and the energy radiation diagram and the windrows diagram. So the wind, the data analysis done is in Amsterdam, the nearest meteorological department available. But as we foresee, the case is going to be a little more towards it, but much more harsh scenario. Since it's in the middle of the sea, we are expecting really high wind. So we started off with a quick sketches of how we proceed to the design, what is most important in our day-to-day life. And we all agreed on one point, that the one thing we always want to be in the center of whatever we do is my workspace, and everything should be accessible from that point onwards. So the design that we are zoning out has the workspace as the heart and everything else as the limbs and hands of it. So the energy-driven approach, we are considering kitchen, another, that we are creating so much of heat, so much of energy dissipation wasting out of the kitchen, but we never use it. So the another idea of zoning out was have kitchen in the center and the whole heat is still retained. So that was more about the site analysis on what was happening on the site. So Dylan will take forward.
For the macro scale, we were given a primitive geometry to begin with, and we we just chose a module to work from. We did some radiation analysis and sunlight hour analysis to give us some feedback to inform how we would adjust our design and let that drive the overall design rather than So one of the aspects of this studio was to integrate locally responsive smart devices for both heating and lighting. Here we have mapping of the usage areas that allowed us to determine the placement of these devices. And here you see our refined geometry based on the information we were able to get from the analysis and the self-feeding loop of the design. Step in here, please.
This was the module which we took from the context and further developed it based on the human body movement and to achieve more user customization. So long story short, we are talking about a structural system which we want to develop further and the devices that we are entertaining into it. So one of the integral devices that we wanted to integrate was a piezoelectric ceramic. So based on the human body movement, it is expected to actuate itself and another devices which we are introducing further. So another one, I mean, this is just a random movement that we would be expecting inside as you enter your house. So the piezoelectric ceramic sensors, they start activating and the actuation further triggers other sensors. So in terms of heating local devices, we are talking about a Peltier device. The idea of using Peltier in this is the internal comfort level is going to be much higher than compared to the external atmospheric and weather condition. It's going to be much colder outside and with electrical and mechanical devices, we're going to take it much way further. So Peltier is a device which would convert heat into electricity and vice versa. So the idea is what you heat, you don't lose it, and what you produce as a heat is used by your body. So there is practically zero loss type of thinking. Another lighting devices which you are talking about in a localized scenario is a microwave motion sensor. The idea of microwave motion sensor is that it triggers the movement, it triggers the lighting devices based on the movement, it analyzes your movement, and based on that it will switch on the lights that you need. Interesting part of that is as you move out of one zone and move into another zone, it doesn't practically just switch off, it goes in a dim mode. So based on your position into the house, it will decide the lighting level at where you are, how much you need in that position, and how much should be there at a point which is at a marginal distance from where you are. And another device we integrated was a DYE sensitized solar cell. The solar cell, which is quite interesting because it doesn't necessarily convert only solar energy into electricity, but it also converts your existing internal artificial lighting into electricity. So one of a kind of device. So with this, we are again targeting a zero energy loss and zero light loss, let's say. In terms of summer, when we're talking about mild to a little warm summers, the temperature again is varying, but you would want to have the external conditions to be enjoyable. So the glass we are using is electrochromic glass panels, so it is possible to change the opacity of the glass and entertain the the sunlight into your house, into the bed, and into the workspaces inside the immediately. So moving to the most important part of what we would rather, let's say, we spend 90% of the time, the zone that we figured out of developing in a 1:1 prototype that you can see hanging on your right side right now. So the idea was to develop a structural system which will be innovative, which will be independent of the regular beam and columns, and it should also entertain, it should also be viable. So the basic study we did was we studied the structural analysis. We ran a simulation based on the stress lines on the structure, and what we found out was the loading and the level of stresses that is going to be existing on the cantilever part, which we are treating as a semi-outdoor open space. I mean, looking further that, okay, we are going to develop something which is outdoor, we're going to have it more porous, we're going to have it more open. We dived into material experimentation starting from cardboard and paper and how we can derive or rather innovate a structural system which is by itself unique, I mean, and it also stands to what we are trying to do. So the system we developed was a triangular panel system which unrolls in itself. The one that we used, obviously, it's unrolled in itself and follows the path, and it is possible to do it on a singly ruled and a doubly ruled surface as well, which was always the target that we were doing, looking out for. So after post-successful experimentation on the paper and basic materials, we thought of diving into the actual material, that's wood. So we dived into the material and we actually were able to sort of successfully do a wooden prototype of the sort of smaller scale of what we wanted to achieve. So that's practically the material with which we wanted to do it in 1:1 scale. The envisioned wooden structural form, how we would wanted it to entwine and stand by itself, the toothing pattern of which we were almost in progress of doing it. Then the next part was a paneling system and porosity integration into the structure, into the design, since it's an outer space. So another criteria which we were targeting since the first workshop with test students was, is it possible to make to bend the wood? Is it possible to make wood transparent? So the image that you see on your bottom, this is entirely the artificial light that penetrates through the wood and passes through the indoor space. The idea was again to have the panels on the windows and have that as transition space from light into porosity. So we again tried various techniques and methodologies which we thought could have helped us. So starting from CNC to milling to laser cut, and eventually we ended up with the robot, and we did the styrofoam cutting and we derived the form. So every element is unique, cut in place. An array of those images, and what we wanted to do was on the right side, and what we have done is on the left side before we mounted it, before we basically suspended. So I believe before suspension, I mean this is just placed elements. They were not tied yet when the photograph was taken yesterday. So I somehow see the idea was a success, and we were able to achieve what we wanted to do. And the future plans of how we wanted to further take this ahead was looking into.
So, coming to the context back to the oil rig, how do you build this macro scale design on site? So, over here we are talking about the technology which we are going to implement for a specific material to express it on site. So maybe
using a CNC method to unroll the flat ridge wooden panels. Originally, part of our design involved a pick-and-place method, but it was something that we abandoned to pursue further development of the ruled surface method. Bending obviously is part of using the flat panels, and then 3D printing was something that we had considered to sort of accommodate the joinery, given the level of detail that we were just not sure what to expect. We would be able to print joinery supplements as needed on site. So the materials that we discussed already, and the methods we just discussed.
So the project cycle, how we had thought we could take into consideration, since it's an abundant oil rig, was we ship into the container. The idea was to have minimal wastage. So every material that we bring in has to be, if it is cast in situ, it goes into the filling part of the rig. And I mean, the idea is to have minimum wastage and a continued loop of a single system of a robot. So like having one labor and having to do all sorts of jobs from picking and placing to detailing out the joineries to fabricating on site. And that's about it. This was the, what's it, to be continued plan. We are firstly very sorry. It was really tiring couple of days, so it was just one of the things.
Thank you for your patience.
Thank you.
Do you want to continue?
Yes, love to.
Oh yeah, and all the models that we discussed and showed you right now are just placed on the table. So
It's okay.
Yeah.
if anyone's keen, you can have it.
Okay. Thank you.
So, yeah, I would like to congratulate you, basically, considering that the time that you had and the fact that you were just confronted with something that it was quite new. I think you did a great job. What I was just talking with one of you before we started the presentation was that what is obvious at the moment that it lacks integration. So if you would have had, let's say, a month, I would say longer, you would have been able to integrate the different parts. So what I was saying is that, for instance, what you can see here is that the openings are, so to say, horizontal and lengthy, while actually the overall patterns, let's say that you can, three-dimensional patterns that you can read here are of a different nature. So starting now, the same also with the structural system. So how does the structural system informs the overall geometry, and also basically these devices, how big are the lights, for instance, how are they distributed, and then again how this feeds back into the overall design. I think this integration, if you would have managed to do, it would have been even more convincing. At the moment, let's say it's still quite divergent in the way it's approached. But I think you did quite a good job in terms of defining the macro. It has quality. So overall, it has qualities, but it lacks integration. That's the way I see it. But once again, congratulations. I think you did a good job.
I think the elements are there, so some wires are not connected.
Yeah.
Maybe. Which
choice of words.
yes. So yeah, I think and the decision that we made about having the mockup in let's say with hot wire cutting, it still can be an informative let's say process for you to define how the overall geometry is detailed, basically.
It actually translates really well because, as you know, and maybe others don't, you're only able to accomplish ruled surfaces with wire cutting, which is the same restriction you would have with using a solid wood panel. So the translation is there. the final product is a bit different, but I think that it proves quite a bit, and
Yeah,
we
and I-
definitely learned quite a bit.
I think, like, for instance, the fact that you modeled your macro scale design with the PSP line, which is completely a different way of representing the geometry, and then when it comes to materialization, you have represented or detailed your geometry with ruled surfaces. This is actually a feedback which would change the macro. So as you said, you have the elements, and actually you have had some feedbacks, and maybe the last feedback, which is really coming from the micro scale to the macro scale to update the morphology or tectonics, is something that in the next experience you would probably have. And yeah, it's good.
Well, yeah, I mean, I was actually happy to hear your comments first, so that I know what's the scope exactly of the research and the project. I've known these guys with me last semester, and I see that I've learned a lot and I've improved a lot. I see that you really focus on the micro scale, as you were saying, 90%, and that was actually the core of your studio here. And I agree that there's things that need to be dealt with in the macro scale, especially when you're talking about the simulation that you have done or analysis that you have done, let's say the solar modes and how their impact on your form or the form you find them. There is some things that are missing there, but and it will emphasize actually your design. You have done really nice research about the materials, about the things that you will start to fill in and use it in your project. I would encourage you, and you have to keep going to wrap up the whole project, to be in a better position, let's say, in a total and the macro scale, overall.
Yeah, and if you do it one time, I think it's very important to do it at least one time, the complete process, because then you're going to see how the design changes, and it becomes more informed, and it becomes more. So at the moment, it's still sketchy because you didn't manage to.
Yeah.
Well, I guess once you have the process settled, you're settled with the process itself, you will be able to, whenever you're going to change the geometry tectonic that you're going to feed in, the whole thing will be adapted to it and will give you a result in the end that will send the feedback to enhance the whole tectonic itself. So,
And one thing I would like to maybe mention with an example, like the way we see the involvement and integration of robotic fabrication, especially at the early stage of design, is different than the way, for instance, we do one-to-one prototyping in practice. So, for instance, if you see I will give you an example. If you see the Hamburg Philharmonic building by Herzog and Demmeren, they also did a one-to-one prototyping of the bed, like doubly curvature glass, right? But it was then a design, not really considering what could happen in reality. And the mock-up is only a way to represent what has been designed. While I think this is like an early mock-up, which is exactly that feedback. When you go again to the, let's say, design and come back to the micro scale, then actually the way you materialize and use any technique of fabrication would be different. So that's why you should not take neither of these processes too literal in the beginning of the project. And in the next iteration, even this way of fabricating or this way of materialization would be different. So this is something that maybe you can think of later on.
I think it's something we definitely internalized late in the process, deep into this last stretch of intense workshop. Almost every time we would get together just to discuss things or recap, it always came back to wanting to do more experiments. So we got the results that I guess we intellectually we're always aware of and knew about this self-feeding or feedback loop, but it really clicked once we were doing actual prototyping and seeing real results and how they apply to the design.
Actually, I think the loop was always there. It's just that it revolved around in the microscale itself. It never came back to the meso and macros. It just revolved in the same stage.
I guess you're aware right now with the loop itself and the whole process of the implemented. So it helps you so much right now. You will revisit that. I guess you will improve the macro scale in a very good way.
Yeah, and maybe a last comment from my side with respect to the posters. So if you want to revise them, I think you may consider to indicate, because you show there, for instance, you do analysis, but it's unclear how, so for instance, environmental analysis or wind, but it's not clear how does this influence the design. Also, you have all these devices and you researched a lot, but we don't know in which way does the architecture change. And I think that even if you make sketches, maybe it's fine for now, and you just state that it was not yet translated into the architectural design. But I think it's because you did all this research, it's a pity to just have it there and with no input almost whatsoever, that it's recognizable. That's it. So I would say that. And one more thing, you learned a lot about using basically wire cutting techniques, but this is also not readable. Also, I liked a lot the movie that you showed, but I think you need to comment it a bit so that somebody who doesn't, it's nice to see it, but what is the particular, let's say,
Yeah. I think that since we have this exhibition on the 14th, I know you're tired now for sure, but like the beginning of next week, we would have some minor comments on mainly the poster and the video to have it defined. We are done with that.
nice one.
Thank you. Thank you.
Prove today that mass customization can be as good and as efficient and as cheap as mass production, and it will even better, it will fit everybody's needs according to their own preferences. This is why our first approach in solving the design problem of student housing is mapping the human activities that happen inside this unit. So our name of this project is Ecological Liability, and by the end you understand what's in this.
First, we had like these three scales, like macro scale and mesoscale and macro scale, and like otherwise, like we try to we have some inputs like the site and the human activity and the student space, which we need. And we had some work to do like in the micro scale. So we started with the micro scale because we wanted the loop, we wanted the micro scale to feed all the whole process, like to feed the whole macro and meso, like again and again, and then we get the prototype from the meso scale. So this is just the workflow of our work. We had like for these three scales, like for the micro scale, we focused on the structure and the porosity of the walls, and also the hybridity between the two materials. For the mesoscale, we tried to find a generic approach to define like these functions in every part of the unit, and also we tried to use the same approach for the macro scale. So for the macro scale, like what we started with is like we started to define like three things, like three main different things. That is the space that the student want, and also the lighting and ventilation that he want, and also the structure, like for his space. So what we started. So first we started to define the 24/7, like every activity of the student. Like we found like there are three main activities, like sleeping and studying, and there is also like meeting other persons. So like we had this idea if we had a space and this space was populated with a cloud point. So when I move and make some activity and sit for a while, I interact with this point. So this point will define the space like that I want. And also for the lighting, like if I am sitting here and the lighting is coming with a cone and approaching me through this point, so this point will define the the location and the direction of the lighting that I want. And for the structure, like if I am using some furniture, like so I want so the load comes from the furniture and supports come under the furniture, and also for the whole space,
Like the movement also can, the frequency of the movement and the positioning according to this analysis will also detect the location of the live loads, and this will help us have a better structure optimized model.
So what we try to do is like we first like we have like every student has 6 main activities like in his life, like sleeping and studying and going to bathroom, like changing his clothes and cooking and also sitting for a while. So we had this like 6 different spaces. We define every space by its area first, and then we define the position of every activity the student made. For example, for sleeping, for the sleeping, the student like is sleeping, and so he is laying on the bed, and then comes up from the bed, so he's just sitting on the edge of the bed. So, like we try to define the movement like he is doing to go to the sleeping. So for the third diagram, you can see like we just define the paths, and we populate the space with a point cloud, and then this paths intersect with this point cloud, so it defines like some points for the space, and also we did the same for the structure and like.
We'll talk into detail on this. For example, this is the basic area, basic generic spaces for sleeping, studying, toilets, dressing, and kitchen. And then we start to populate these not populate first, sorry. First we start to introduce the positions, the average positions of the persons that are using these spaces, and then trying to see the entire domain of the movement inside all of these spaces, where I'm gonna possibly use the space, the air inside the space, and then we're going to populate all of these volumes with the points, and then see the intersections between the movements, and then we have our geometry, our map geometry. This inside this geometry is the actual maximum domain and maximum range of movement for each single activity. And by the same approach, we're going to detect the locations of the supports and loads based on the furniture, the fixed furniture as dead loads, and the people as live loads. And then we also took the lighting as another parameter that we're going to introduce. For example, in the bed and in the study and all the other spaces, we need different amount of lux on different spaces according to the sub-activities inside each of these spaces. For example, in the study, for example, I don't need lighting coming directly on my computer screen, and on the other hand, I need light coming directly from in front of me if I was writing or sketching. So these are all the factors that we introduce. So this is the first type of mapping that we have done inside each single activity. Then the second mapping that we introduced is the mapping that relates all the activities inside the whole unit together. And this would help us also develop a system that would take this as an input and then generate an optimized configuration between all of these map geometries. For example, let's see here the study. If I'm in the study space, I go to the study space just one. Like, imagine that this is 0. And then I go to the bed space 3 times. And kitchen 3 times, and toilet 2 times, lounge 4 times, dresser 2 times. If we add all of these values, we'll have 16. We'll call this factor frequency weight. And then we have applied this same approach to the 6 spaces that we have inside the housing unit in order for us to detect which is the most frequent space inside. And accordingly, we have done a system that will take this as an input, and it works in iterations. First of all, it puts a study in a center of space that's also populated with points. And then it starts to subtract the points that are inside the study and then detects the closest points outside it in order to add the next most frequent activity, which is the lounge. And then third iteration will take both the study and the lounge and detect the average frequency between all of them. For example, iteration 3, the bed, doesn't come directly to the study. It comes in space between the lounge and the study because the bed comes in third place according to the frequency weight, and then its location is based on its frequency between the study and the lounge. So this would help us generate a more informed and better optimized space. If we've done the whole iterations on all the spaces, we get this result, this map geometry, and this would help us create the basic geometry or the basic primitive geometry for our housing units. Yeah, so after that we started defining the geometry more and solving it architecturally from inside and outside. These are the plans. These are the sections. So this is the end for the macro scale. As for the mesoscale, maybe some talk about it.
Okay, to continue the same concept of defining the characteristics of the space based on the point clouds, we did the same, but for part of the study of our study unit.
Since it was the most frequent and most important space that we have.
Yeah, so we defined firstly the space points that define the whole space of the disk and the working area, and then we start to put the supports and loads based on the live loads and dead loads. Then we did an analysis for the stress lines and topology optimization, and then applied it to the same point clouds. And same as for the lighting and ventilation and heating. So at the last we came up with our maybe complex point cloud, that each point in this cloud has its own characteristics based on the previous mapping for lighting, ventilation, and so on. So
So as a conclusion of all of these, for example, we said we have structure lines that we need to respect. So we have introduced reinforcements. Let's say I will get into materiality later, but let's say we introduced reinforcements in the areas that we need in the areas that we have structural loads. And this is not directly related to the structural loads that we have defined before. This is related to a structural analysis that took these loads as input and then generated the stress lines. And then we started working with these stress lines and introducing the lighting and ventilation and heating points that we have discussed before to create some sort of repulsors, to create openings between all of these branches. So, for example, if we take any of these branches as an example, each of them has a specific purpose to provide lighting and ventilation and heating for the space that we are working on. And then we have started to introduce an envelope around these reinforcements with the EPS. And of course, after that, in order to think about production, we'll cut them into smaller components, according also to the stress lines, in order to avoid having a cut right within the stress line, so it would be structurally stable. Yeah, so this is a porosity that would help us provide all of the mapping that we have talked about. And of course, we have introduced the hybridity because we are working now with two materials. We have used for reinforcement. We have used concrete for reinforcement, and EPS just as an envelope material. So we have introduced a hybrid material between them basically, and what made all of this possible is that we have a new robotic tool that will help us achieve all of this. And this is the assembly based on the components cuts, of course. And one more thing that we have added is that after you have introduced porosity and after you have introduced all of these openings and reinforcements, you still need to optimize the space more and you still need to achieve your required goals. So we have also introduced smart devices such as LED lights in areas that maybe sometimes the lighting, the maximum lighting that will go through these holes or through this porous hybrid system would not be enough or would not be sufficient to achieve our mapping requirements. So we introduced that, and we have also introduced smart ventilators to control the in and out ventilation, and we have also introduced motion sensors. And this is the EPS and the branch concrete inside to show the hybrid. This is the final meso design. This is just a component of the wall inside the study area. And we took it further to develop it more and study it more and see the exact requirements that we need. And then we have reached the micro scale, which is the smallest scale we have.
Yeah, like we said before, we want all the micro scale to feed the whole process, like for the macro and the meso. So when we first we worked on our project, we did some material experiments on concrete and EBS, and we first defined some matrix for these experiments. Like we have some factors these factors is the hybridity and porosity and structure, and also the behavior of material of the material we are using. And also we have some variables to control the volume and the orientation. So we had this matrix between this the three between the factors and the variables. So we tried to reduce we did so many experiments, but we didn't put them all in the end. We just select some
the one that we learned most from.
Yeah. So we selected the most experiments that had this type of hybridity and porosity. So for the lot no for that. For the first one, go back. So I need to explain it first. For the first one, we just used the white EBS, and we reduced some inner space inside it using some acetone. So and solving this foam, and then we tried to put some concrete inside it, and we got some part as a column, and it has small tectonics with the foam. So we might use the foam as a domain for the tectonics of the concrete. And for this one, we tried to form for the last one we did it's a vertical one. Here we had it has a non-linear shape.
We just wanted to experiment the relationship between the concrete and the foam visually and structurally. And these are the results that we have come, and these results have strongly inspired the way we think about hybridity.
And for the most successful one, this one, we tried to produce a column, it was a hybrid column between the EBS and the concrete. And so we tried to create some pores inside this EBS and tried to pour some concrete inside it to enhance the physical structural strength of the EBS.
These are more examples of what we have done and what we have experimented with. Yeah, okay. So the componential logic, basically, as we have said before, we have thought about the actual way for construction. So in order for us to have the hybridity and the porosity, and of course the concrete and the foam, all of them together, achieving all of this, we have to think about how the robot would actually do it. So we have basically cut them into 4 subcomponents, let's say. First, 2 components are the 2 in the middle, which are the main enclosure or mold for the concrete, and it's also enclosed by the 2 outer ones as a temporary mold. So in order for us to achieve the visual quality of the concrete showing from the surface, coming out of the surface of the home and inside again. And this is also the model with porosity, and clearly shows the concrete in green, light green, protruding out of the foam, and all of it as hybrid material. And we can also see a sample of the concrete cast over there. And this is the final hybrid component that we have designed.
So you can see these concrete branches, like it comes out from the foam. So we have a hybrid surface between the concrete and the EBS, and also these branches, like enhancing the structural physics of this part of the component of the EBS, and also like we use the inner spaces between the lines we used to create these concrete branches to put some porosity inside the foam, so we can have some openings and small ventilation part.
So coming to actual construction, we have started doing the molds through milling, and by the way that we have explained before, through 4 components. And then after the milling, we have taken out the molds and properly sealed them in order to avoid any leakage of concrete inside the foam, so it wouldn't stick when we remove the temporary molds. And these are pictures of showing the process of preparing the molds and then mixing the concrete, and then the final closing sealing of the mold and casting. And this is the final mold prototype that we have used. Okay, so now just have a video, just a summary and showing the construction process. Just show it. Just a quick summary, so the mapping. It's not good speed. It's not good speed. These are the iterations that we have spoken about.
Which software do you use?
Hmm?
Which software do you use?
Russell.
Russell.
This is the primitive geometry that we have included. And this is after refinement, showing the plans and sections. and square sections. And 1 plus 1 and 2 sections. So the same process we have also applied for a fragment of the study, just to refine the mapping and refine the results. This is the final combined mapping. This is the components with all the labels and the porosity and smart devices. This is the final four component part, and the assembled one, the product should be right in the middle, with the pink as concrete and the white as foam. This is a diagrammatic representation. And this is the milling, summary of the milling process. And so as you see here, it's basically a subtractive process. So
So I think it's a great project. As I told you already. But I have still some questions, and I still think that you could integrate more what you develop now at the componential level. How is it going to inform the overall design? Because it's the way I appreciate also the aesthetics that it has. But maybe before you integrate, it's worthwhile to have a look at the component, because one of the questions is, what is the, based on what criteria did you decide where is concrete and where is EPS? Because if you consider inside, outside, you most probably are going to think that we don't want a lot of concrete outside, we want more inside, etc. So this is one of the questions. And also, you talked about the devices, which I thought it was very important, because this has been lacking, let's say. But we don't see yet, for instance, cables. And I think if you would manage to, maybe not for this project, but if you manage to introduce even that, and especially in your project with this approach that you have, which is quite, it has parts that are very thin and filigree. So they could complement each other. It's very consistent. So and then it would become very complete and unified and strong, I would say.
To continue with the question of Margarita, I think we have, when it comes to this research-driven design approach, we have maybe 4 terms to think about. One is representation, be able to represent and show disability. One is computation, be able to compute where to put what and why. We have fabrication, be able to actually produce disability. And at the end, we have design, right? So if you think of the first 3, so with the experiments that we have had, be able to actually produce a hybrid system. For instance, we were thinking that if in material world, the 2 materials should be isotropic, means that they should be continuous. So that was a constraint or criteria for in terms of materiality or fabrication. And in terms of computation and representation, so you did a great job of to actually have this hybridity, right? But when it comes to design, I think based on all these research that you do, you may need to take some decisions that is based on all these studies that we do in terms of representation, computation, and fabrication. That is missing, especially when we want to talk about or work with components, because still a componential logic is missing in your design. So maybe based on all these experiences that you have gained, and I would argue that they are consistent, because at multiple scales you are talking about like pixels or voxels in different resolutions, and all these resolutions are somehow connected, but not maybe directly connected. And that's where you need to design, start designing and elaborating this further. Yeah, but in general, I think things are connected. And in macro scale, another thing that maybe also applies to other group is that so the fact that we let's say divide or categorize the design into 3 scales, like macro, meso, micro, especially when it comes to this, let's say, towards the end of the process, we may not actually follow this linear way of presenting from macro, meso to micro. But this is just a suggestion. I mean, I'm not saying this because we have this in cinema, like if you see a movie first, the last scene is shown, and then go back, this is a feedback. So this is, of course, a technique of presentation.
This is what I talked about in the first slide. Like we said that the micro sometimes give
Yeah,
us
yeah,
feedback.
but that was
macro-
not visual, right?
Yeah.
That can help.
We did so in the poster, but for the presentation we wanted to be so linear
consistent.
for the
In order for the
So I'm not talking about the method of presentation. I'm talking about the method of thinking.
Right.
So if you could defend or connect to the final result at the beginning, this shows that actually there was a feedback and it was not linear. Which in your case, in my opinion, it was not linear, right? So this is something that maybe in your video or poster you can think about it and work on it further.
2 more things. And this I mentioned already at midterm, because you have basically this orthogonal space that you start with. And it's interesting because I was yesterday giving a presentation in Den Haag, and there was I was presenting with somebody from Cornell University who presented basically an interactive piece of furniture. And it was basically a table, and it was a rectangular table. And the lady in the audience said, why do you bother actually having an interactive table when, which is supposed to service better people, when actually we know that the rectangular table is not ergonomic. So you want basically a table somehow that is more fitting to the activity that you have. And I'm saying that why? Because at midterm I was telling you that if you say this is the space and you map the behavior, of course the behavior that I'm mapping is in relationship to the space. So this is so you should do also the exercise the other way around, because at the moment, let's say the methodology is extremely detailed and very well done, I would say, but certain assumptions are a bit of a shortcut. So, and then you always are going to get criticism, basically, because you have extremely developed parts, but certain assumptions are so simplistic that everybody is going to see that.
And it would be hard actually to keep the very initial geometry or topology and with this level of detail go back to, so That's why the very initial assumption or hypothesis you also mentioned in the first part, which was a theoretical hypothesis about mass customization, we need to be able to hammer and change this hypothesis without any, let's say, but we have to easily be able to change these initial assumptions. And what is more important is actually the process that we are in and the next step that we are heading for.
So maybe your assumption is
Or your, let's say, if you can see, like, we try first to make a generic mapping on like a similar space for everyone. Then, like, after we designed
we understood that you don't need to ignore because I think everybody understood that.
yeah, we tried to use not the same furniture. We tried to integrate the furniture in an ergonomic way.
Yes, yes,
Then,
yes.
and we
We
did
see
the
that.
mapping again on this, like, on this
Yes.
part, yeah.
Yes, that's correct. But you,
To go back.
yeah, I know. But you want to say something?
Yes, and I wouldn't add for the fabrication part because I guess we have done a really good job and we already have given really good feedback. I would actually, I like your hypothesis or your thesis, what you want to really achieve, and the way that you started to work with this point down. And I would say, I mean, things have to do something in your presentation as well as the best way to present this process is to show a simulation rather than still images, because we look at them and we are not quite sure actually what would happen in between one phase and then the other one and so on. Then when it comes to a simulation, also the choice of the software actually helps you actually much more. I mean, I know that you have learned a lot in this, focused a lot in these 3 months to learn a lot about the application part. But for you in the future, for example, the software like processing, for example, will be super helpful for you to achieve how to layer all of these different phases on top of each other and start to come up with a kind of 3D mesh out of it. And it's going to be kind of a looping process. As much as you're going to change the input, the whole output will keep on generating for you a different output. But then it comes to the process or the criteria of choosing. It's still, we cannot see it here. It's, you have your intentions about it, but somehow what you have got as a shell or as a form is still not the optimum one. And the simulation process for us as an architect, when we're simulating something for as computing for a design, is not a watertight thing. I mean, your impact for it is very important. After that, many times we take these forms and we have to, work in it, remodel it, and make it more aesthetically beautiful. As far as it's as a simulation works with all the aspects that you need, and it's okay, verify your criteria, but you still need to have your impact. I know it's a 3-month semester and it's a lot to achieve. Your project is very ambitious. I really like it so much. But it needs more time actually to do all of these things.
Yes, basically to have porosity in overall design, windows, doors, etc. So, and then have transitions from the very big openings to the very small openings. So, and I think you have the ingredients. So, if you manage to do that, it's going to be an excellent project.
Just a quick question. I guess this project more about forming as a whole object rather than a component based, or
Yeah, it's all about, like, we never do a component separate than the design. So the design challenges the component differential scale and differential scale challenge the design skills is the.
So it's a feedback loop basically. So we never look at things separately. So we may study them separately, but in principle we try to always establish.
Maybe we are actually missing that one extra month that we haven't.
Yes, I think so too.
But yeah.
And one more thing, I think you can improve the video. Don't make it like a PowerPoint presentation. So certain things you don't need to show. So make it.
And that some part of the robotic fabrication was actually two-dimensional, which we were discussing in the lunchtime. But it's interesting that how the structural information is actually needed to be able to fabricate something. So I would include that in the video, which is more two-dimensional.
I would encourage you to look at references, for example, PRL, for example, how they present the output of the simulation of the process itself. and it will need from you some After Effects and some skills and some create a kind of one scene, like make all your simulation very connected to each other, so the whole process we get in the end and the conclusion as a one thing, wrapped up.
Especially in video, I would not go for a linear approach. I would start from the prototype, for instance. So you need to come with a storyboard.
Simulations. Yeah. Well done.
Thank you.
Thank you.
Okay.
So hi guys, I'm TJ and here my roommates Shijong and Aris. So to start with the project, we would like to talk about the things that we personally are interested in, which is to find out some sort of different architecture, and the architecture is discrete architecture here. It's about like stacking different layers of material with one another, and then it forms some sort of form. And with that said, we actually explore into the ideas of very, very simple stacking techniques that architects like Tengu Kuma uses in a very grid form, or even in a very traditional way to form a facade or even a structure. So here we have is a single linear stack, and then when you give a twist, you have a different form, a more fluid form. And if let's say you were to stack in a form of a grid, you can actually branch out in three-dimensional. So with this kind of thinking in mind, we kind of give a parameter to the design by introducing three types of students for a unit. So in general, would be a baseline between the two extremes, and then these are the things that we have done. Yeah. So by using the Da Vinci's Vitruvius Man kind of a method, we kind of map out a very basic geometry of students based on dressing space, and then sitting space. Sitting would be working, and then free space would be spaces that connecting different spaces within a room, and as well as sleeping. Three of us has different type. So in a way, the formation is being done based on our own experience of our room. So Qizhong would be the general students, I would say, the one that fits both in being open and being enclosure. And then Aries would be the one that is the extrovert, in a way more likely to interact with people, and I would be the one that is very much close in my own room when I'm in my house. So the generation for students and general student type would be placed above the overall structure, meaning the moment when you come in from the entrance, you walk through the living space and then you have your own privacy at the top. So that would be how, that's how we actually place the general student. And then the extrovert would be more of just entering into the living space, directly connecting into the own spaces. While extrovert is very very close to the entrance, so you walk in, you don't see anybody, and then that's how you get the deal. And the type of student that we are gonna work on is a general one because it covers many different. I mean, it's exposed first of all, it's exposed to environmental factor that is not being blocked up because it's being placed above, and then the type of spaces is also equally balanced compared to the two extreme. So with that said, we were given a site which is an oil rig in Netherlands, and then based on that environment that is given, we use the analysis that is provided to come up with the radiation analysis based on the general model, the sun path coming up from east to the west. So the darkest part would be the hottest part of the day, while the whitest part would be intact to the main block of the building. Same radiation analysis and rules that we get. So based on all these environmental factors and parameters that we applied to the building, and also based on the feedback that a user would request, like where the windows would be, and then where you want to have the view, how you apply it, like how will you map the heating or maybe cooling system, artificial lighting for spaces. For instance, this main space would be the dressing room, and then this small space here would be the sleeping, and this would be the working space. With all these informations and data, clumping into the block, we will actually get a formation of colors like that. So if you were to look at the yellow ones represents sunrise. So obviously you want to have like a window that's facing sunrise, while the red here is actually radiation, which is the west side of the sun, whereby you would actually want to cover them. And the purple would be heating and cooling system, and the light blue that you see at the bottom is how we actually implement ventilation, that we want to map them at the bottom of the building so that air comes in from the top, from the bottom, and rise up to the top. So this would be the parameters that we are going to follow. Or continuing the mesoscale, which is to select a wall. We have selected a wall on the working space because that space itself is the most populated zone that we get. So from that on, we actually analyzed the stress line, gave it the geometry, and then from the stress line, we extruded and parametrically extruded the stress line and to give it a volume so that the structure would stand, and then populate some sort of a block, very simple block structure, while the inverted part of it, the void part of the structure would be the porosity, which is going to be in a smaller scale because it's supposed to hold no weight. And from then on, a vertically stacked member, we actually divided this whole wall into 3 sections, pick one wall to work on. While on the side of picking this wall, we actually found out, you can actually twist and turn these components based on the needs that is required. So, for instance, if this were to face upwards, it would actually react really well with sun, and then if you were to have it straight, it would actually give more sense of view, while at the bottom it would bring up the ventilation. So, based on the component, we actually have to think about a sort of a joining system. So the only thing that is going to be an extra piece or maybe a custom piece is based on the angles that is being joined from one component to another. That would be a more of a custom made of based on direction, so that it joins in 3 parts interlock to one another. And then for the porosity, we played I mean, we did an experiment, but now this is a digital sketch of what we've done. Of what happens if you were to stack big blocks of bars on one another. How would you play with the voids in between by inserting smaller components? And what happens if you actually have smaller components to be on its own? And the type of details that we incorporate is that whatever you see here, the bigger, call it 5 cm, the bigger bars are actually the size ratio three times bigger than the smaller one, so that when you stack them, it aligns in a way in a parallel form, so that you don't have items or maybe bars that is actually floating. And also, like it's mentioned here, twisting angle versus length. So when you have an extruding length, how much can you actually introduce a twist in a grid system so much that it wouldn't have any collision? And also, on the side, actually, this twisting and all is actually introduced based on the parameters that we are allowed to set. So for instance, if you would like an opening in a grid, the grid will actually follow you based on an attractor point, so that it opens based on where you're sitting, and then you can have like a full 360 view in a way. Integration of smart material, we are actually utilizing the fact that these sticks can be used as a solar panel on outside when it's being extruded. It holds no weight, it can actually be a whole component of a solar bar, while the inside of the material could be an LED that lights up the space. And also kinetic responsive membrane or component means that it responds based on your action. Wherever you move, it can be introduced in a way that it follows your angle. And this would be
piezoelectric polymer, which can detect human body motion. When you generate some motion, that actually can generate electricity for the overall spaces. So the next one is a Peltier thermal, as we are all using. It's kind of a device that heats up the interior with the electricity control.
So this is a section for smart material, and we'll dive in straight to prototyping based on the selection that we have done. So, like I mentioned, type of stacking that we would like to introduce so that we reduce the amount of floating bars or maybe even collision based on the angles that we apply. We found out that, if you were to twist, give it a little twist, and then you were to put the porosity in between, it would fill up the gap while provide porosity for the structures. And the way of fabrication would be pick and place. To pick up the bar from one corner, have it cut, apply glue on it, and then place it as little as that. These are some of the photos and some of the porosity on the side. As you can see, the thick ones are the structures, and then slowly introducing more and more porosity until it's dense on the side. The walls we have selected, top view, some of the details. Basically, you should walk around and just take a look at this. This is actually a part of the table. And we also have a video of our production. there won't be any soundtrack, so there's no sound. So let's enjoy this awkward video. So we have a secondary robot on the side. That's about it. Thanks.
Well, thank you for the presentation. I was actually telling Sina that this is like the interpretation of Rietveld. You know Rietveld actually used Mondrian's paintings and reinterpreted them three-dimensionally. So he used basically only rectangular surfaces or basically bars like these ones. And he used only primary colors. So you should look it up because it's an interesting reference for you. And I think it's an interesting project that you managed to develop, and I wanted to thank you for mapping the zones, because I was asking this for quite a lot of time, and you were the only group who managed to do that. And I think it's, of course, you mapped the zones, but what we don't see yet is how they inform the design, also in relationship to your stacking approach. Yeah? So I think if you could somehow try to establish a feedback loop, and I think this is also obvious in the macro impression that you have there, that it's a bit
Maybe on that.
Yeah.
Which again maybe goes back to that one lens that we don't have here. But beside that, another reason is that system comes at the very end of the design, and I would say there is a reason for that, because if you compare this project in terms of computational design technique and parametric design to other two projects, actually the other two projects, first we have the geometry or form, and then we do the analysis. And through analysis we define the material tectonic, and the material tectonics will be translated into fabrication, and fabrication feedback with feedback. While this one, actually, the very first constraint, or there should be an embedded constant while you're generating the form or while you're generating the material system. It's not like you generate the form and you can populate any kind of configuration of the bars, because of physics, because of sequence of assembly, which we also experienced in the production, let's say, stage. So, and yeah, to answer this question of critique, I think one of the reasons that the process of generation of the form is really based on these constraints. And actually, the more you work with these constraints and embed it in your parametric systems, the more flexibility you have, which obviously at this stage, because you're only working on with one set of constraints, this has resulted into some sort of restriction to refine the overall geometry. So, but well, as I said, it's a nice effort that you did, and you can continue this later to work with this constraint-driven design. And actually, in the work by Killian, if you search, he has explained very well how actually the constraint can be a design variable. Later on, you can have a look at some creative applications of this idea in his works.
So, for instance, of course, from the if we think of what could be, let's say, two extreme conditions that you could investigate, at least in addition to this one where everything is almost enclosed and you have almost no porosity, and one where you have a higher degree of porosity than you have now. So at least two more conditions would already help to have, let's say, a more architectural approach. Because you would want to have complete enclosures, you would want to have also windows, for instance. So can you work with this system towards pushing it towards having an architectural? At the moment, let's say it's at the beginning. It's promising, it has quality. Of course, at one moment in time, you will need to reflect if this would be relevant for an architectural design that would be implemented in real life, or what would you extract from it, and how would you implement it. But for now, I think even having basically this range from very enclosed wall to a very porous wall would be already a contribution to this investigation.
Another further elaboration of this is that, okay, now we are putting more or less standard elements, but different sizes, different angles. If you want to really design with this system in the next iteration, you can imagine that actually each of these components are produced by a robot, and then the process of assembly and compiling these elements together would be different. It will give you on some levels more freedom, but on some levels some introduce another layer of constraints which you need to work with it. Yeah, and but in general, I think all of the designs shows this idea of systemic thinking and how different parts of the design are connected together, and to which extent they are deterministic. I want to just maybe just tell this story because, like, when we were stacking this, so everything was tagged and aligned, and through this human-robot collaboration, only one of the elements was flipped 180 degrees. So, and everything was collapsed because we couldn't trace back the algorithm, and it cost us 2 hours, right? So it's really interesting to think like systematically about the design, but at the same time, I think we as humans sometimes we need to intervene this process of it's a deterministic approach, and on top of this, again, go back to computation, fabrication, and the presentation, we are in charge and we are the designer, not the algorithm. So,
they choose really interesting system as a stacking things on top of each other, but it's very challenging to work with it in a three-dimensional transfer from a fluid to a skin into a slab. It's very challenging to create a surface with it. It uses it as a universal system.
Yes, this is what actually we started by trying to have, so to go away from a generic system, but it was a bit too challenging, right? So we were trying to specialize the components, but it didn't happen this night. So, but
I would say if we push it more outside the Cartesian X and Y and Z and start to dive more into the kind of the norms of the algorithm, go out of these three dimensions, will I guess actually create more interesting with narrowing or like using the stacking instead of the sticks. Maybe the component was getting more smaller to be able to control somehow. Would actually create very interesting topography coming out of the shape.
yeah, I agree with that. So basically, initially we started with this idea, but it was too challenging.
And
I think it was too big, the step was too big. So this is why we went back to this one, and basically next time when you do a project, maybe that can take us to the next step.
And this goes to the fact that, I mean, theoretically everything is possible with robot as far as you make it possible. Even maybe it's not visible, but we know in the process of assembly, one may see this as like a more traditional way of assembling things, which is not, which you see a cantilever here, which is against gravity, right? Actually, through the process, we understood that actually the sequence of assembly and creating counterbalance weight is important. So, from research point of view, definitely there are interesting, let's say, aspects that we can push further and think about. And that research, on one hand, feedback to the design, but at design level, having some leap or jump would help us to change the way actually we do research about this.
We see a lot of work being done here. I see how challenging it is. I see how much you put in it to counter the gravity. Really interesting, very interesting research. It just from you really to challenge it more and develop it in a way to feel at the time. So you have done also really good job.
Yeah. One more advice for you, maybe for this short time, maybe it helps if you scale up. So just for feed it back into the design, because I think there is a, so if I look at that, I don't think it works. Trying to scale it up, or just for the purpose of this exercise, see if it works better. Because this is a way to. So is this 1-to-1?
This is 2-to-1. Yeah, because of the robotic prefer.
But maybe it should be 2-to-1. As I said, 2-to-1 should be 1-to-1.
Yeah, because like as I said, everything is robots.
Because, and if you look at this, you can achieve like
curvature,
and
tectonic and stuff like that.
So probably if you want
Thank you.
It's very interesting.
Camera to robots and tag these things in
place it. I think I've seen this before. We have seen this before.
But it's not like it's not completely predetermined what the form will be. Form can be generated.